Hi, my name is Rafael. I'm studying electrical engineering, and at this time I am focusing on transformers. And I want to bring to you what I've understood about transformers. And in addition, I want to review the subject so I can be better on the drill. So let's see what we can understand in this first lesson. Single-phase transformers. Lesson 1. In the figure, I tried to show a transformer core and a winding wound over one of the cores. One of the arms of the core. So, at the left arm of the core, there is a winding. What happens if we apply a sinusoidal voltage at the terminals of this winding? It's represented by the voltage E of t, which is the voltage source. Let's imagine that this source is sinusoidal. It varies with time. And I represented the resistance of the wires connecting the source to the winding with the letter R, which is a resistor. The resistor represents the resistance of the wires, or an internal resistance of the source. If we apply KVL, which is Kirchhoff voltage law, we're going to see that E of t, the voltage of the source, equals the voltage drop on the resistor and a voltage on the windings, across the windings. We are interested in the voltage that builds in the winding, EL of t. How does this voltage build up? It's what we are trying to understand. It's the law of induction. The law of induction. You can further Google it if you find it necessary, but the law of induction simply says that if we apply a varying current to pass through the wires of that winding, which is a solenoid, an inductor. For us, it's just wires wound on an arm of a core. If you already studied magnetic fields, you promptly say that when we apply a current to pass through the wires of a winding, there is going to be a magnetic field. Alright, but this magnetic field will spread itself, will flow over the core. It's what we want to build, the concept that we want to build. But, the double integral of the magnetic density, which is related to the magnetic field, you can see on that expression that B, which is the magnetic density, equals Ni times the intensity of the magnetic field. This Ni depends on the core. it's a property of the core called permeability. If the core has a high permeability, let's say it's an iron, the permeability of the iron is much higher than the air. If we wound this wire about an iron core, the permeability will be very high. So if we make the double integral of the permeability, which is a constant, times the magnitude of the magnetic field through a surface, we're gonna get phi. Phi is the flux, and according to the induction law, this voltage that builds up on the winding, it's proportional to the number of turns times the derivative of phi in time, in relation to time. So this is how this voltage builds up. It's proportional to the number of turns and d phi dt. But this phi, this flux, it happens only if there is current. But if our current is DC, or if our voltage source which makes the current is DC, d phi dt will be 0. And what we're gonna get? A short circuit. The inductor for DC sources, it becomes a short circuit. But for varying currents, it allows voltage to build. So if the current is DC, d phi dt will be 0, and no voltage will build up. But if d phi dt, if the current is varying, a sinusoidal current, d phi dt will be a number, and it will allow the voltage to build up. Okay, so this is what I wanted to show you today. Alright, I hope you've understood what I wanted to bring about. If you didn't understand at all at first, see it one more time and maybe you will understand a little bit better. If you do not understand or want further explanation, just Google it and you'll see a lot of other explanations about it. Bye bye.